Okay, welcome back to the energy analysis of closed systems, which we were discussing. This is the last part of this particular module. So we were discussing the specific heat of ideal gas. Okay, and this particular module we are going to discuss a bit more, and then we'll discuss the incompressible part and followed by some example. Okay, so let me summarize what we have learned about specific heat relation for the ideal gas. We know from the definition that H is equal to U plus RT. We already defined that for an ideal gas, U is a function of only T and H is a function of only T. So if you take a derivative of H or this particular expression, you obtained this expression, which is dH is equal to du plus R dt. Now, considering the fact that U is just a function of temperature and H is a function of temperature, you can replace dH by simply dP dt. So this is just an ordinary differentiation. Okay, the partial differentiation gets replaced by ordinary differentiation because of the fact that U and H is constant. Thus, you can obtain a relation between Cp and Cv, okay, by plugging this here. So what you get is a relation of Cp and Cv. So you can obtain Cv, and from there you can also get Cp, but these are related by the gas constant. Now this you can write also in a molar basis. Okay, this is kilojoules per kg Kelvin, and hence if you convert R to a universal gas constant, you get kilojoules per kilomole, and this represent molar basis. If you have the information of Cv, you can obtain Cp. Or the same thing, if you have the information of molar specific heat at a constant volume, you can also get molar specific heat at constant pressure. So Cp of an ideal gas can be determined from knowledge of Cv and R. One of the important parameter which is commonly used to analyze gases is the ratio of the specific heat, that is called K. Okay, so specific heat ratio is K is equal to Cv by Cv. Okay, and this is interesting because if you look at this ratio for many gases, it is constant. For example, for monoatomic gas, its value is essentially constant. So you can relate this to the original picture or the graph which we have used in the last lecture, where we showed that for monoatomic gas, the Cp at very low pressure is almost constant with temperature. But otherwise the variation is very mild, okay, for other gases. Okay, for the case of a diatomic gases such as air, the specific heat ratio is around 1.4. So let's do some example here, okay, and let's make use of the last lecture summary, the way which we different ways to calculate the change in the internal energy enthalpy. So this is an example to calculate change of enthalpy for 1 kg of oxygen, which is heated from, and what we have to assume is ideal gas behavior. Okay, so as I said, there are different ways to calculate. So we will try two ways here. One is calculating directly delta H from the table. Now for the case of oxygen, the table which is relevant is A19, and this table, the H is given on molar basis. So delta H for the case of this 300 to 1500 will be on the molar basis based on the table A19, and the values are 49292 minus 8736 kilojoules kilomole. If you want to convert this into mass basis, then essentially you can divide by the molar mass, which for the case of oxygen is, so this is the value divided by 31.999, this becomes kilojoules per kg. So this value turns out to be 1267.375 kilojoules per kg. Or, so this is one way to obtain the change in enthalpy. So you directly made use of the table. So again we are going to calculate delta H. Okay, so here what we are going to do is we are going to make use of A2 table, where the values are given in terms of polynomial function, and you can evaluate Cp value. Okay, so Cp is given in terms of polynomial function, but in terms of molar basis. So this is a second way of calculating delta H. We are going to make use of A2, and delta H bar is given as Cp dt. As I said, we are going to make use of table. The tables is mainly written into this form. So irrespective of whichever textbook you pick up, you will find this kind of fate for the Cp values. Okay, so this temperature is from 300 Kelvin to 1500 Kelvin. And so without showing the details of the calculation, it turns out that delta H, okay, is around 1241.5 kilojoules. Okay, so this is much more, the first method is much more accurate, and this is not so, but still is very accurate compared. If you look at the difference is extremely small. So these are the different ways to solve problems. So we will take another example. This is a cylinder fitted with a piston which has an initial volume of 0.1 meter cube, which contains nitrogen, okay, which is at 150 kilopascal and is 25 degrees Celsius. Okay, the piston is moved, compressing the nitrogen until the pressure is 1 megapascal and the temperature is 150 degrees Celsius. So essentially it is being compressed such that the temperature is increased and as well as pressure. Now during this compression process, heat is transferred from the nitrogen and the work done on this nitrogen is 20 kilojoules. So what we have to find out is the amount of this heat transfer. There are two ways to do this problem. One is, of course, you can simply write E in minus E out, okay, equal to delta E. Okay, so this is one way where we know the net energy provided to the system and net energy which is transferred out of the system. Okay, so or the other way we can make use of a standard sign convention where you say that, well, Q minus W is your delta E, and in this case the work is done on the system. So essentially Q minus 20 kilojoules, because this definition is Q which is supplied to the system minus work which is done by the system on the surrounding should be equal to change in the energy of the system. Okay, so this should be equal to m u2 minus u1, considering the all other terms such as kinetic energy and potential energies are 0. So this is one way of putting it. So if I had used this, I would be using E in, which is work done on the nitrogen is 20 kilojoules minus Q out, okay, is equal to delta E. So this is one way where we just write out because we know the sign of it, okay, but otherwise we can make use of a generalized form where Q is what is being supplied to the system minus work which is done by the system on the surrounding, and which is minus 20 kilojoules, because the system now here in this case surrounding does work on the system, that's why it should be minus. Now, so we are assuming Q is supplied to the system, that's why we put Q here, so we will know with the sign. So what about now mass? What is the mass here? And so we can calculate the mass here. M is simply PV by RT. Okay, we are assuming nitrogen to be ideal gas. Okay, so this is initial mass is because mass would be fixed, so we have the information of 150 kilopascal into volume, which is 0.1 initial volume, okay, and R and T. R, you can obtain R from the tables. So R is the gas constant, so you can look at A1 and from there you can obtain 150 kilopascal into 0.1 meter cube and 0.2968 kilojoules per kg Kelvin into 298.15 Kelvin. Okay, so this is the R value from the table, and based on that the value comes out to be 0.165 kg. So mass we know. Now the next thing is how to find the change in internal energy. So we can write Q plus 20 kilojoules is equal to 0.1695, and delta U can be written as CV, some average, considering the difference here we will take an average here, so some average, let's say C2 minus C1. Okay, so what we can do is we can look at the tables, and first we find out CV at a specific T average, which is going to be T2 plus T1 divided by 2, and from the table this value comes out to be 0.744. So T2 plus T1 by 2 is nothing but 360.5 Kelvin. Okay, so this is the value which we are going to make use of it, and from here you plug in this value. T2 is your 150 degrees Celsius, and this one is 25 degrees Celsius. You can convert this into Kelvin, but being a difference between two temperature, this is not going to make any difference. So the Q value turns out to be minus 4.23 kilojoules, which essentially means there is a transfer from the system, okay, to surrounding, okay, as of course the question was mentioning. So without taking the direction from the question, if we solve it, the answer turns out to reflect the direction of the heat transfer. This was an example. We made use of the fact that the CV average can be calculated by taking the temperature average of the final initial values. Since the values are not dramatically, it doesn't change with temperature, so this approximation is okay. So this was an example of that. Now let's pay attention to different system. Here we are going to consider substances which are incompressible, which means a substance whose specific volume is constant, and these are examples are solids and liquids. So that for such system one can show mathematically that specific heats are constant, which essentially means CV is same as Cp. We are going to just denote by C for the case of solids and liquids. So considering the fact that C and Cv are same, one can also show that for the case of such system, just like ideal gas, your C only depends on temperature. So thus you can find out the change in internal energy by simply integrating C over a temperature range from state 1 to state 2. Okay, or you can approximate again, as we have done that for the gases, in this form. Okay, where you can approximate C average over the temperature range. Okay, so let's now look at specifically enthalpy changes for the case of incompressible substance. As we know, H is equal to U plus PV. That's a definition. So you can differentiate, and so it will be dH is equal to du. Then it will be, there will be two terms because you can differentiate first P and then you later V. Now considering incompressible substance, this part is going to be 0. Okay, so what remains is du plus VdP. Now you can integrate this and get your du to get your delta U and VdP. Now VdP, we'll talk about VdP later, but delta U you can replace by C average delta T as an approximation. So this would be your enthalpy change for incompressible substance. Okay, for solid it turns out that this term is extremely small. So this is specific volume, it typically is very small. This was also illustrated here in terms of that. So this is typically very small, thus your delta H is simply your C average delta T. But this term is need not be very small for the liquids. So let's look at this change in enthalpy for liquids. So again we start with the same expression. Okay, now there are two specific cases. Okay, the first case we are going to consider a constant pressure process, okay, where we can consider delta P to be 0. In that case your change in enthalpy is simply your C average delta T. The other case we are going to consider where your temperature is constant, that means your delta T is 0, which means the first term is going to be 0 and delta H is equal to V delta P. Now if you recall, earlier we've approximated for the compressed liquid the change in enthalpy to its saturated liquid values, okay, at a given temperature. So that was an earlier approximation, okay, but if you consider this, the information that delta H can be related to V delta P, and you say this is simply as V F at T, and this would be your P2 minus P1, okay, and your 1 could be your saturated liquid, okay, and this could be your compressed liquid. So this would be your at P1, okay, or saturated condition. So you can make use of this and plug in here to obtain your H at a specific P. Okay, so this is nothing but your H2 minus H1. H1 is your saturated liquid values and H2 is your specific compressed liquid. So thus you can write in this form, this is your compressed liquid. This can be approximated now that this is nothing but the values at saturated liquid plus this term, which is going to be the values which we are considering volume, specific volume to be constant, and the change in the pressure. So this you can understand from a PV diagram. Okay, so this is your for the pure substance, and this is at a constant temperature. So liquid, and it evaporates at a constant temperature. Okay, when you reduce the pressure. So what we are assuming is that you, for the specific PT, which is, let's say, this, okay, this is the, you are interested in this particular enthalpy at this P and T, you are assuming that this can be approximated by this value plus the change in the pressure, okay, delta P, multiplied by corresponding V for the specific T here, which is this. Okay, so this is the reason being is that you can look at the slope here is very high, assuming that the volume is not changing upon increasing the pressure by delta P. So this is a more accurate relation which we are going to use it for the case of liquid. So let's take a look of an example, try to finish this module with an example. So this is an example of 50 kg iron block at 80 degree Celsius, which is dropped in an insulated tank, and which contains 0.5 meter cube of liquid water at 25 degrees Celsius. Okay, so this iron block is being placed in the water, which was at higher temperature, and it is, the whole tank is insulated, and then you have to find out the final temperature of the system. Okay, so let's look at how we're going to solve. So we'll take the generalized energy balance here, E in minus E out is equal to E system. Now upon dropping the iron block, the system is insulated. So after that, of course, there is no change in the energy which is being provided to the system, or there is no transfer of energy from the system. Thus your E in should be 0, and as well as E out should be 0, because once it's insulated, the system is not getting any energy from the surrounding, and as well as the system is not transferring any energy to the surrounding. So thus this X is 0, and what remains is nothing but delta U. We are of course ignoring other terms. So delta U is 0, okay, which means the change in the internal energy of the system should remain 0, U should be constant. So what is U? U is a extensive property. So delta U system contains, there are two species here, or two components, one is iron and one is water. So it should be your delta U for iron plus delta U for water. Okay, so that should be 0. This is a solid and this is of course liquid. So we are going to make use of specific heat. It can be written as MC for iron and T2 minus T1. Okay, for specific iron. So let's say this is for iron plus MC T2 minus T1. Okay, or this is for water. So this T2 and T1 are respective temperatures of initial and the final state for iron and water. C is basically the respective specific heat for iron and water. Okay, now you need these values in order to solve the problem. You also need the mass here. We know the mass of iron, but what about the mass for water? We know the density of the water, or we can make use of that and obtain the specific volume. So what is the specific volume for water? Would be 0.001 meter cube by kg. Okay, thus your mass for water is going to be volume divided by specific volume, which is going to be 0.5 meter cube by 0.001 meter cube by kg. So this is going to be 500 kg. Now the next thing which we are going to use is a table to obtain the specific heat for iron and water. So the table which contains this is A3, and then we plug in these values, because now we know the mass of iron, C of iron from table 3. So let me write it down here, 50 kg, and the value from table for the case of iron for specific heat is 0.45, T2 minus 80. Initially the iron was at 80. What is the final temperature? That, let's say, is T2 plus 500 into 4.18 kilojoules per kg specific heat for water, and this is going to be T2 minus 25 degree Celsius. Okay, and this should be 0. So if you solve this, T2 turns out to be 25.6 degrees Celsius. So that's how we're going to solve such a problem, making use of the specific heat. Okay, so let me summarize this particular module. So we described boundary work for different processes. That was the initial part of this particular module. Then we looked into the energy balance for closed systems. Then we described specific heat for ideal gas for different specific heat, one as constant pressure, one at constant volume. Okay, and then we relate this Cp and Cv values in terms of relation for ideal gas. Then we mentioned that Cp and Cv is constant for incompressible substance, and later we solved an example. So that will be the end of this particular module. So we will continue with a new chapter. So see you in the next lecture.